Hello, my name is Michael, and in this video I want to give you an overview of my lecture, which is called Introduction to High Performance Computing. Here at Ulm University, the math department is actually offering more than just one lecture on this topic, high performance computing. It's a complete series consisting of 3 lectures, and this introduction lecture is the first lecture in this series. So our lecture this semester is the first lecture in this series, so we're talking about this year, and for this lecture I want to give you an overview about the content. But I think it's a good idea to understand, or at least have a glimpse of understanding, why we are covering this content. What is the purpose of it? So let's begin to talk about the content of the last lecture, very briefly. In short, you can say the purpose of HPC2 will be the numerical treatment of problems that matter in the real life. That's how I like to explain it to other people outside the university. To you, I can say these are problems from fluid dynamics, for example. In short, you can say problems from engineering and physics. So, for example, you are dealing with the Navier-Stokes equations. What all these problems have in common is that we only know in theory that some unique solution exists. But until today, at least, we haven't found a way to write down this solution on a piece of paper. So we don't know the analytical solution to this problem. But of course, we know how to deal with such problems. In lectures for the numerical treatment of partial differential equations, you are introduced to numerical methods that can be implemented on a computer so that you can find approximate solutions to this problem. And for a given threshold, these approximate solutions will lie within a certain error bound. And you also learn how to formulate a numerical algorithm for a numerical method. And algorithm means that you can implement it on a computer. That means in the end you have a computer program that computes an approximate solution to this problem. And this approximate solution satisfies a certain given error tolerance. And then from the theory in numerical partial differential equations, it's also obvious that if you require a smaller error, it requires more computational time. That means the program will run longer if you want to have a better approximation. So we're also dealing with the performance aspect in this numerical lectures. But in high-performance computing, the focus is a bit different. We will use these numerical methods and these numerical algorithms, but we are in particular interested in exploiting the computational performance that is available from a certain given architecture. And in order to understand now the actual problem, you have to have an idea what kind of architectures are there. Let's begin simple. Assume we can solve the problem with one computer. Then we come up with the idea to buy a second computer, same type, and then we connect both computers together with a network. Then you can't expect that the program is out of the box just running twice as fast. You have to modify this program so that it's exploiting this new architecture, this we would say cluster of compute nodes. And for that, in order to change the program, you have to come up with a new algorithm. In the simplest cases, it would be just computer number 1, you solve the first half of the problem, computer number 2, you solve the second half of the problem. But in more interesting problem settings, you can't solve the parts of the problem independent of each other, so you have to think about how much communication is necessary and how can I do this efficiently. And this requires really some understanding from the beginning. Sometimes you have to choose a completely different numerical method which can be better adapted to this new architecture. And another example would be nowadays you just can buy computers with 4 CPU cores or more. But in the beginning, in good old days, you bought a computer with 1 CPU which had 1 CPU core. And then came computers up that had 2 CPU cores, and this didn't mean that programs out of the box were running twice as fast. You had to modify the programs, which requires to modify the algorithms. And in our case, if we want to exploit multi-core architectures, we also have to think about what is different in this architecture compared to another architecture, what kind of method is appropriate for that, what method can exploit this architecture. Here, for example, communications costs would be not that expensive because communication is not going over the network. Things like that we have to incorporate. But in short, HPC2 is dealing more with the mathematical aspect that is required to exploit a certain architecture. So you already should know more about the details of these architectures that I just briefly scratched. And dealing with the architectures on its own is topic of HPC1. So we're talking now about this lecture here in the middle. The problem types in HPC1 will be much simpler compared to what I told you about HPC2. For example, solving a system of linear equations where the coefficient matrix is dense. But of course, the dimensions of these matrices that we're dealing with in HPC1 will be large. So the type of problem mathematically is simple, but the challenge is still there. And here in HPC1, the focus will be on the different type of architectures, how to formulate algorithms that take advantage of these architectures, of their special features, how to overcome certain problems, that certain challenges, and of course also how can you implement these algorithms, because we want to see results. Of course, this is also true for HPC2. You also want to see results there. You also have to implement your algorithms. But in HPC2, you already had HPC1, so the technical skills are already there. So in HPC2, you can focus more on the math because the implementation is not that a big deal anymore. In HPC1, the focus is really also on how do you do the programming for exploiting different architectures. And just to mention some cool thing, in HPC1 we will always compare ourselves with others that are dealing with the same kind of problem on different architectures. And for example, Intel provides a library called Intel Math Kernel Library, and then we will compare in benchmarks our results with Intel. And spoiler alert, we are doing well. So now we come to the actual topic of this video, HPC0 Introduction to High Performance Computing. Well, what's the topic of HPC0? It's giving you the necessary foundations for HPC1 and HPC2. Okay, that's short, but of course, now the question is, what are the necessary foundations? Well, first of all, you should understand how a simple computer works. I mean, before we go to a cluster of compute nodes, where each compute node has a multi-core CPU and maybe also some GPU, graphics processing unit, we should understand how a simple computer with just one CPU and one CPU core, of course, works. And what are the other relevant parts for an actual computer? What is the simplest thing that we need to have something that can be called a computer and that can be programmed? And in order to understand that, we will build our own computer. We will use as building blocks so-called logic gates. So these logic gates will be the smallest type of building block that we will use for building our computer. And we will not go below that. We will not deal with how you use transistors for building a logic gate, but of course we also have lectures for that. So using these logic gates, for example, one of the first projects will be building something called an ALU, an arithmetical logical unit, which is a relevant part of a CPU. And then on top of that, we will build other things that are relevant for a computer that can be programmed like the computer you're sitting in front of right now, but as simple as possible. And then we can program our own computer. One of the first programs will be a Hello World program, of course. And you will write this program in machine code. That means you will write a sequence of zeros and ones. Actually, you can represent it in hexadecimal. You will see this will save some typing. And don't worry, you will understand how to do that. It will be not that big of a deal. But once you have written your first Hello World program in machine code on your own computer, you will realize that actually for programming this computer, you don't have to know each and every detail about it. Basically, you can say the knowledge about your computer can be divided into two parts. One part is relevant for programming it, and we will call this the instruction set architecture that is implemented by your computer. And this implementation of this instruction set architecture with, for example, logic gates, that's the microarchitecture which is realizing what is necessary for the programming. Now the consequences are as follows. You could change the microarchitecture, and a program that was running before on your computer and was printing Hello World would still do the same. That means if you improve the microarchitecture, the program still works, but maybe it runs faster. So you can speed up already existing programs without the need to rewrite them. And I already told you before that in HPC1 we will deal in more detail with the microarchitectures that are actually out there and available on computers that you can buy. And then you will see, okay, for actually programming it, if I'm just interested in the result, I don't have to change my program, I don't have to know about the microarchitecture. But actually, if you want to exploit the performance, sometimes you can use this knowledge in your algorithms. So you actually write a new program, not because you have to, but because you want to, because you want to make it faster. So this is something different. So the microarchitecture is only covered in the beginning of these lectures when we are dealing with these logic gates. In order to get a reference implementation for our computer that is realizing a certain instruction set architecture. But then the main focus of this lecture is actually programming this computer and programming computers in general. As I said before, the first program that we write for our own computer will be in machine code. But the purpose of this lecture is to teach you how to program a computer with the programming language C. So for us, C will be a high-level language. Other people probably would call C a low-level language. But if you start with machine code, you will see C is a very easy way to express things, more convenient. And let me outline how we go from machine code to C code. In the beginning, this Hello World program will be easy peasy, no problem. But then you will realize if things become more complex, if you want to do something which is more interesting than just printing Hello World, it's easy to find bugs. It's taking a lot of patience and discipline to write a program in machine code, but it's possible. But there is a more convenient way to write programs in machine code. For each machine instruction, you have an equivalent symbolic representation called the assembly representation of this instruction. And although it's completely equivalent to each other, it's for us better to understand because, for example, if the instruction is adding something, the assembly representation is probably called add something. So if we look at code written in this assembly notation, if we look at assembly code, it's easier for us to understand what this code is supposed to do. And also you can use comments in this code so that you actually can remember the structure of the program if you look at it a week later or so. And using this assembly notation and assembly code, I will show you certain patterns for realizing things like loops, for loops, do loops, while loops, for realizing functions with parameters and local variables. So basically everything that is there in C, I can show you in form of patterns, how to apply patterns to realize that directly in assembly code. Then we can do a cool project, and this will be also not as hard as it sounds. I will provide you C code as pseudocode and this bunch of rules, how to apply certain patterns, so that you can look at the C code and translate it into assembly code so that it runs on our computer. And one project, for example, will be that I provide you C code for the quicksort algorithm. So basically the C code is supposed to be a pseudocode for you. Others would say this is already an implementation. And you will write then this quicksort C code in assembly directly. That means I give you some C code, you apply certain rules, and then you produce assembly code. That means you are a C compiler, because that's exactly what a C compiler is doing. Once we have reached this level of understanding that translating C code into assembly code is just applying a tedious sequence of dumb rules, we could just write a program which is doing that for us. I mean, that's the next step, of course. And actually, I already did that for you. I have written a C compiler for this instruction set architecture. That means from that point on, you can directly use the C programming language to do what you before had to do in assembly code. So from then on, you can use my C compiler to write programs in C for your computer. And one cool program that you could write would be a program that translates C code into assembly code, your own C compiler. But for a complete C compiler, the semester is probably not long enough. But if you choose instead a language which is much simpler than C, still C-like, we could write a compiler in a reasonable amount of time. And you still would basically learn the most relevant things. How a compiler works in principle. You learn a lot about data structures and the C programming language itself. And also what kind of errors can be detected by a compiler and what kind of errors cannot be detected by a compiler. Very helpful when you're doing programming, to understand the compiler errors and to understand what kind of errors you have to catch by test suites that you have to write by yourself. Another thing that I could have mentioned already before, once you reach this level where you can translate C code into assembly code, you most likely will come to me and tell me, okay, you gave us these rules, that's why I have to translate this C code into this assembly code. But if I instead would translate it into some other assembly code that has fewer instructions, it still would have the same effect, but it would be more efficient because it has fewer instructions. And that's perfect, because that means then you already have found some way to optimize the compiler, the code produced by the compiler. And that's usually the point where we start to discuss compiler optimizations. What are the requirements for them? What are the possibilities? So, understanding how a computer works by building a computer, understanding how a computer can be programmed, ideally by writing your own compiler, are the main topics in this lecture. Something third will be done in between. We will not actually build computers in hardware. We will use computers, and on these computers we will run a simulation of our computer, which could be, if you have enough patience, done in hardware instead. But we will use simulation software for logic gates. We will use a virtual implementation of our computer. That means actually it's not a computer in hardware, it's a software implementation of what we are coming up with. So you have to use already existing computers, and we will not use graphical user interfaces much. For the logic gates we actually do, a web interface actually, but for the programming part we will stick on the old school way of programming, which is done in a terminal, actually in a Unix shell. So learning how to work on a Unix machine is another topic. So using the Unix shell, invoking a compiler from the command line, understanding all its options, writing makefiles, using a text editor that doesn't require a graphical user interface. These are just a few other things that you learn in between. I think for a video that is just a teaser for the lecture, this is enough, so I say goodbye.